Now this time, let's use differentials to approximate the square root of 3.96. We'll use the same function. F of x is equal to the square root of x. Let's set x equal to 4, which is a convenient number that's close to 3.96. It's easy to evaluate the square root of 4, with the result being y equals 2. Now if x is changed from 4 to 3.96, then dx, which is delta x, is 3.96 minus 4. The new x value minus the old x value. We start with 4, the old x value, because it's the convenient number, so that it would also be easy to evaluate the derivative f prime at 4. Now f prime is of course 1 over 2 the square root of x. dy is equal to f prime of x times dx. So therefore dy is 1 over 2 square root of x, the derivative, multiplied by dx. X is 4 and dx is negative 0.04. The resulting dy value is therefore negative 0.01. Now what this is an approximation to how much the y-coordinate will change from its original value of 2. When we add negative 0.01 to y equal to 2, we then get 1.99 as our approximation to the square root of 3.96. This is the same estimate when we used a linear approximation earlier. Whether you use differentials or a linear approximation to estimate the value of a function, you should get the same answer since they are both based on the same tangent line. Before continuing further, keep in mind derivatives and differentials are related, but they are different. For example, suppose y equals sine of x. The derivative dy over dx is the cosine of x. Multiply by dx, which is the differential of the independent variable, and we get the differential dy, which is cosine x times dx. Finding dy involves differentiating the function, but with one final step, which is multiplying by dx. Now, also, I cautioned you back then not to interpret the notation dy over dx as a fraction until we have identified what the numerator and denominator are. Well, this time we've done that. Dy over dx is actually a fraction. It's actually a quotient, the quotient of two differentials, with the differential of y defined precisely as f prime of x times dx, so that the quotient of the two differentials, dy over dx, is the derivative f prime. Suppose s of t equals t cubed minus 4t, the position function of an object moving along a line. The derivative is 3t squared minus 4. Multiplying by dt gives the differential ds. If s is in meters and t is in seconds, then ds over dt will be in meters per second. Just remember, ds over dt is the velocity. However, multiplying the derivative in meters per second by dt, which is in seconds, turns the unit into just meters. After all, ds approximates the change in s, which is in meters. So again, derivatives and differentials are related to each other, but they are different. Next example. The radius of a sphere was measured as 21 centimeters, with a possible error in measurement of at most 0.05 centimeters. Use differentials to estimate the maximum error in using this radius to compute the volume of the sphere. Now, our measurements are only as good as our measuring devices. The actual radius could be as low as 20.95 centimeters or as high as 21.05 centimeters. The actual volume could thus deviate from what a radius of 21 would give us. Now, the volume of a sphere is given by V of r, equal to 4/3 pi r to the third power. The radius, currently the baseline, is 21. But the change in r, delta r, has absolute value at most 0.05. Note that delta r can be negative, so that's why you have the absolute values there. The resulting error in the volume is delta V. Let's approximate this delta V using dV, the differential of V. By definition, it's the derivative of V, which is 4 pi r squared, multiplied by dr. Replace r by 21 and dr by the magnitude 0.05. To 3 decimal places, 277.088. The error in the volume is therefore at most 277.088 cubic centimeters. This means if you compute the volume using the potentially fake radius r equal to 21, you may have to go lower than this by up to 277.088 or higher than this by up to 277.088 to arrive at the actual volume. Follow-up task. Find the relative error. By definition, this is the magnitude of the largest possible error compared to the computed volume if R was actually 21. So what you could do is use 277.088 as the numerator, and the denominator V will be 4/3 pi r cubed, where R is replaced by 21. Or alternatively, you could use the algebraic expressions 4 pi r squared over dr for the numerator dv divided by the volume 4/3 pi r cubed. Simplifying this results in 3 over r dr, and replace r by 21 and dr by 0.05, and that would give us 0.0071. Or in some cases, percentages are preferable. The percent error is 0.71%. Now, before we go to other examples, it would be helpful if we can visualize them as part of further comprehending what differentials mean. A square with side s has area a equal to s squared. If the side is changed by an amount ds, then dA estimates the change in the area. dA therefore estimates the area of the region shaded in blue. Now a circle with radius r has area a equal to pi r squared. If the radius is increased by dr, then the circle gets slightly larger, and the additional area added is estimated by dA, shaded in blue. Now I also have here the circumference, c equals 2 pi r. For the original circle with radius r, the circumference is represented by the red dashed circle, which you can see as the inner lining, unrolled here on the floor as this red dashed segment. Increasing the radius by dr produces a larger circle with circumference represented by the green dashed circle, the outer lining. When unrolled, you then get this longer green segment. The difference in length, the difference in the circumference, is denoted by dc, the change in circumference. Next, we have a sphere with radius r. Pretend it's our planet even if our planet is not really a sphere. If we increase the radius by dr, say we want to include the atmosphere, then the volume increases. You could imagine that this added volume, estimated by dV, is the volume of just the Earth's atmosphere. All right, For our next example, a metal box in the form of a cube is to have an interior volume of 64 cubic inches. The six sides are to be made of metal 1/8 of an inch thick. If the cost of the metal to be used is 8 cents per cubic inch, use differentials to find the approximate cost of the metal to be used in the manufacture of the box. It's 8 cents per cubic inch. So first, let's estimate the volume of just the box itself. Specifically, we need just the casing itself, excluding the hollow air in the interior of the box. The volume of the metal casing is the difference of the volumes of two cubes. The smaller cube has volume 64 cubic inches, so the side length is 4 since the volume V of S is S cubed. The larger cube extends all the way to the outer lining of the metal casing, with side length larger than 4. But by how much? This is ds. Is ds equal to 1/8 of an inch? Be careful. Each side is increased not just on one end, but also on the other end. Are you able to imagine this? Therefore, ds is not 1/8, but actually double 1/8, which is 1/4. Now let's proceed. The volume of the metal casing is the difference in volumes of the smaller and larger cubes I described earlier, estimated by dV equal to 3s squared times ds. Let's plug in the values of s and ds, 4 and 1/4 respectively, and we get 12. For comparison, the actual difference in volumes is actually 4.25 cubed minus 4 cubed. So the actual exact volume is 12.765625, comparing with the estimate from the differentials, which is 12. It's not a bad estimate. Okay, let's continue. So therefore, using 12 cubic inches as our estimate for the volume of just the metal casing, the total cost is approximately 8 cents times that. So it's 96 cents. For the next examples, I will just provide you with the answers. I'd like you to try to figure things out on your own first. Assume, contrary to fact, that the Earth is a perfect sphere with a radius of 4,000 miles. The volume of ice at the North and South poles is estimated to be about 8 million cubic miles. If this ice were melted, and if the resulting water were distributed uniformly over the globe, approximately what would be the depth of the added water at any point of the Earth? After the ice caps are melted, the Earth becomes larger in volume. This change in volume, 8 million cubic miles, corresponds to dV. The increase in sea level is dr, the increase in the radius of the planet. What is dr? You can pause the video if you want to try this problem now. For the answer, dr is approximately 0.0397887 miles. Did you get the same answer? Multiplying this answer by 5,280 gives us, to the nearest integer, 210 feet as the rise in sea level. Next problem. Suppose that a rope surrounds the Earth at the equator. The rope is lengthened by 10 feet. By about how much is the rope raised above the Earth? Even though the Earth is approximated as a sphere, the rope is wrapped around the equator, a circle. So the length of the rope is a circumference c. What does 10 feet represent? Do you see that 10 feet is the value of dc, the differential of the circumference? And what is it that we're looking for here? We want to find dr. You can pause the video if you want to try this problem now. The answer is 1.59 feet. That's the end of this discussion.